Welcome back. So now we're going to continue on with chapter 9.2, in which we're going to talk about the natural numbers, whole numbers, and integers. These are some fancy names for sets that we're used to working with. We'll start with natural numbers first. Another name that we call the natural numbers is also the counting numbers. And just as counting implies, it's kind of like when you play hide and go seek. You start at 1, 2, 3, and you keep on counting to whatever your limit was. For the natural numbers, there's no end. You keep on going in that fashion. So after 3 is 4, after 4 is 5, and you keep on going. And what I've written here is a ... That's an ellipses. And that says continue on in that fashion. And the natural numbers we describe using a black boldface N to equal this set, and that's what the curly brackets stand for, of numbers 1, 2, 3, and keep on going. Since we don't only work with the counting numbers, we have more numbers out there. We had to develop more sets of numbers. The next one is the whole numbers, in which the whole numbers include all of the naturals, and also includes 0. It's important that we have 0 in our whole numbers because 0 represents nothing to us. So that's where this set comes into play. So we start at 0 and we work our way up. We have 1, 2, 3, 4, keep on going until you can't count anymore. It's very important it starts with 0. And the way we denote this set is with a black boldface W. Now, integers come about because, we have counting numbers, we have 0 to represent nothing, but we also have to include our negative numbers. So we have negatives, and pretty much we're also including all of the whole numbers in here. So it's the negatives and the whole numbers. Now, the set's going to write a little bit differently because negative numbers, we can get really, really small numbers out there. So I start with an ellipses, and we could continue on and say, okay, we have -2, -1, we're at 0, we're at 1, 2, 3, keep on going until you can't count anymore, and there's our set. So the ellipses on the right side, we know what that means because we just saw it twice. After 3, we continue on to 4, we continue on to 5, and so forth. On the other side, what I have the ellipses there for is, notice we went -1, -2, the next one will be -3, -4, and those are the set of our integers. And now you might think we'd use an I to represent it, but we don't. For some reason, we like to have a Z to represent the integers. So those are our 3 main sets of numbers that we work with, the integers being the primary one we like. There is also a more bigger set in which we have the rational numbers. Now, the rational numbers, once again, is a funky, we're going to call him Q. And bear with me as I write this set notation. So we have the set of pretty much fractions, A over B, such that A and B are integers. So from the previous set we just introduced. And then there's one extra thing here. B cannot be 0. We'll close our set. So let me give you a good example of a rational number. Think of any integer. I like -3. And then I'm going to put it over another integer because that's what the directions are saying. A and B are integers. As long as B is not 0, we're okay. So something other than 0 needs to be on the bottom. Maybe, 22. So -3 22ths is a rational number. Done. Alright, let's try another one. So maybe you like 1. I don't know if you do, but we'll give it a shot. So we have 1 for A, and something other than 0 for B. So how about, 1? Well, 1 over 1 is really 1. 1 is a rational number. It doesn't have to have the exact view of a fraction. It just has to be able to be written as a fraction in order for it to be a rational number. Now, non-rational numbers, we call them irrational. And we'll go more into them later. Essentially, if b ever pops down into the bottom, that's not allowed. And then there's some things that can't be written as fractions, so we'll see them shortly. What I want to go ahead and give you an overview of our real numbers, which was the title of this section, real numbers. So the real numbers breaks into two categories. We have the rationals, which we just experienced, and then the ones that are kind of flaky to us, we call them the irrationals. And since they're so hard to write what exactly an irrational, we'll just think of them as not rational. And that will keep our viewpoint for now until we can expand it further. Now, rational pretty much includes all of the integers. And all the integers include the whole numbers. And all the whole numbers include our natural counting numbers. So there's our hierarchy. We have rational and irrational as the breaking up the two parts of our real numbers, and then rational just gets more specific. Pretty much integers where we like to work, and then we'll see fractions and decimals a lot for the rationals. To expand on the rationals, what we are going to do is talk about fractions more. And fractions are very interesting for the rationals. We can write them as decimals. And there's two types of decimals these fractions can turn into. Either they are a terminating, and I'm going to squeeze that in hopefully, that says terminating, or they are a repeating. And in case you can't quite read my terrible handwriting, I'm going to go to the next page in which I wrote this out nicely. So we have terminating decimals and repeating decimals. These are fractions for us that can be written a little bit differently. So I'm going to give us a nice example of what a terminating decimal is. This is a rational number. So I have an integer, say 7, over another integer, say 4. And what I'm going to do is view this fraction as a decimal. If it ends, then I can say it's rational. So let's go ahead and see. We got 4 is the number on the bottom, so he goes on the outside. 7 is the number up top, so he goes on the inside. Add a decimal point, line them up, fling some zeros at the end of it. Doesn't matter how many you put because they're insignificant. You can add or subtract zeros depending on your needs. And you go, what times 4 will get us close to 7? And 1 is the closest you'll get. 7 minus 4 is 3. Let's bring down a 0. We don't have to worry about that decimal point since we already lined them up. So we pretend it's not there essentially. And 4 times what gets us close to 30? And that is 7. We have 28. Subtract, we got 2. Bring down the 0. And 4 times 5 gets us 20 even. No remainder. We don't have to keep on bringing down zeros since we've reached an end. Hence the name terminating decimal. So we've changed this fraction into a terminating decimal, and it is a rational number. Now if we wanted to get a little bit crazy, we could look at a repeating decimal. And one that we can look at is 7/11. Once more, it doesn't matter which number is bigger. It's whatever number's on the bottom tells us how to divide. 11 is dividing into 7. Add a decimal point. Let me just add 1 0. I'll add more if I need them, okay? So I'll line up my decimal points. Now, 11 times nothing gets us close to 7, so that's kind of silly. We won't bother with that. And then we'll move on and say what times 11 will get us close to 70, which is 6 for 66. Subtract. We got 4. All right, since I didn't end with 0, I'll add another one, bring it down. 11 times what gets us close to 40? And 3 is correct. We got 33. And I need a little bit more space, so let's see. Okay. Subtract, we got 7. I didn't end with a 0, so I'll toss down another 0. And 11 times what gets us close to 70? And now you might be noticing the pattern. I don't see it yet, so I'm going to say 6, so 66. Subtract, we got 4. I'll fling another 0 at the end. It doesn't matter how many we put there, they're insignificant. 11 times 3 is the closest we'll get, and now we definitely should be able to see a pattern going on here. We're repeating 6, 3, 6, 3. You can see we got 70, then 40, 70, then 40, and it just continues on in this fashion. So I wrote the ellipses saying continues on in this fashion. Now the proper way we're going to write this is 0.63 repeating. And that bar there is for repeating 6-3 over and over. This brings into some very critical notation, okay? So I'm going to switch to a new page, and I want you to be very careful of your notation. So if we have something like 0.222 keeps on going until you're blue in the face, the proper way to write this is 0.2 repeating. It is not good to write 0.22 with a bar over top. That's repetitive. We already are writing a repeating notation. We don't need to repeat what's already been said. It's silly. 2 repeating is just saying the same thing as 2 repeating. So do not write that. You also want to be very careful of something like this, 0.61111, and that 1 is repeating. Notice the 6 is only stated once, and then it's the 1 that's repeating itself. So when we write this notation, we have 0.6 with a no bar over it. The 1 has the bar over it. Only the 1 is repeating, so only it has the bar over top. If you were to have something like our previous problem where we had 6-3, 6-3, 6-3, notice both of them are repeating themselves. So now we need the bar to cover over both integers. So be very careful. If you have more questions about that, you can always come see me in office hours. The next one we're going to talk about is order. So in order to get order clear to us, what I'm going to do is draw what we call a number line. And number lines are much straighter. I'm sure I can cheat and use this tool. Oh, that's very clean. We'll do that instead. So here's our number line. Now, the number line, usually we like to start at 0, somewhere plop in the middle. And when we head towards the right, we go positive. So we increase. We go 1, 2, 3, keep on going until you can't go anymore. And continues on in that fashion. And if we go to the left, we go -1, -2, and keeps on going in that fashion. So we can kind of devise an order here. When we go smaller, we go to the left. That's usually where our negatives lie. They tend to be much smaller than our positives, which go to the right, in which they get bigger. So when we want to compare two things to one another, we are going to use inequalities. And the two main symbols we're going to talk about is, first, the is less than, and the second one, which I already drew there, is greater than. Now I have a little bit of a childish way to remember these. I kind of think they look like gator faces. So here's the eye, we got some teeth, and the gator is hungry, so he always faces towards the larger number because he wants the bigger guy. So let's start with two integers. We'll be nice to ourselves. Let's say 1 and 1,000. So this is an example. Now let me ask you, and I won't tell you the answer, I'll give you a second to guess it. Which one's bigger, 1 or 1,000? And kind of think about it. Would you rather have $1 or would you rather have $1,000? And I personally would rather have $1,000, or maybe this alligator is eating, I don't know, fish. Would he rather have 1 fish or 1,000 fish? And he's a very hungry alligator, so he'd rather have 1,000 fish. So his mouth faces towards the bigger one. The way we read it is 1 is less than 1,000. And if we could write the same statement a little bit different. Let's say 1,000 we were comparing to 1. So we're saying, okay, 1,000, we already determined we'd prefer $1,000 over $1, or the alligator would want 1,000 fish over 1 fish. So the mouth is facing towards the bigger guy, and we read it as 1,000 is greater than 1. Now we'll go ahead and do some examples. So we're going to use either a less than or a greater than to make a statement true. And we have 13 compared to 0. So you can always draw it on your number line, or you could ask yourself, would you rather have $13 or would you rather have $0? And I would rather have money, so 13 is bigger. So we use the 13 is greater than 0. The negatives are kind of a little bit more tougher. So what I'm going to do is draw that number line again. And let's say here's -5, -6, -7, -8. All right, so there's our visual representation, and we're comparing -8 to -5. I also like to think about it in the money sense. Negatives imply I owe somebody money. I either owe $8 or I owe $5. I'd rather owe $5. Unless you're crazy and you want to give out more money. That's up to you. But -5 is much larger than -8. 5 is smaller than 8. I agree with you there. But when we talk about two negatives, the further to the right on the number line, the bigger it is. And -5 is much further to the right. So the alligator faces towards -5. Now these fractions, which are kind of a little scary, not super bad. We're comparing -1/7 to -2/5. There's quite a few ways you could do this. The two that I will mention is you either make the fractions into decimals and compare the decimals, or you stick with the fractions and you make them have the same denominator. We want to compare the same denominators to one another. So in order to compare fractions, we need a common denominator. Between 7 and 5, the common denominator, least common denominator, is 35. So what we're going to do is take -1/7 and get it so that we have a denominator of 35. 7 times what gets us 35? Well, 5. So 1 times 5, and it's both negative, so we have -5 35ths. And we'll do the same thing for -2/5, in which we go, what times 5 will get us 35? And you already know it's 7. So then 2 times 7 is 14, and it's still negative. Now that the denominators are the same, we can just look at the numerators. We're comparing -5 to -14. And it kind of goes back to our previous problem. The smaller number that's negative is actually larger. I'd rather owe $5 than owe 14. So let's see, then that means -1/7 is much larger than -2/5. Alrighty. Continuing on, we have to write true or false to satisfy these statements. Now I have two new symbols involved here. We have less than or equal to. So is less than or equal. And then the other guy, the flipped version, is basically is greater than or equal to. So I'm going to shorthand my handwriting here, greater than or equal. Okay, there's our two new symbols. That line on the bottom is what's causing the or equal to part. Now, because it's an or statement, it means one or the other has to be true. So I'm going to write this inequality two ways. We have -5 is greater than -3, or, oh, I did magic there, or -5 is equal to -3. Only one of them has to be true to make the whole thing true. Okay? As long as one is true, the statement is true. If both are false, then the whole thing is false. So let's see. Is -5 greater than -3? Let's see. They're both negative, so the smaller negative is bigger. So -3 would be technically bigger. So this isn't true. Okay, now let's go over here. Does -5 equal -3? No, crazy talk. So both of them are not true. That means it is false. And my F got a little screwed up. There we go. Now let's look at the other guy. We have 3 is less than 3, or 3 is equal to 3. That's how we're viewing it. As long as one is true, it makes the whole statement true. Is 3 less than 3? No. 3 is the same as 3. 3 equals 3. Aha, that is true. So one of them's true, that makes the entire statement true. Okay? If both turned out to be true, which is next to impossible, yeah, it's impossible. Both can't be true. Only one of them will end up being true. All right. The next thing we're going to talk about is the absolute value. The absolute value is the distance from 0 on the real number line. And distance is always positive. And usually how we read it is where we have these 2 straight bars, something inside of it, and we read it as the absolute value of x. It is very important for us to understand whatever's inside the absolute values is the only thing we're taking the absolute value of. Anything on the outside, fair game to stay the same, okay? So only worry about the inside of absolute values. Let's see some examples. The directions ask us to find the absolute value of a real number. We have -69 inside the absolute value. So the absolute value of -69 is measuring the distance from 0, which pretty much just makes everything positive. So when we take the absolute value, whatever's on the inside just becomes positive. That's to say, if we had something similar, let's say we were finding the absolute value of 69. Well, I mean, it's already positive, but it doesn't matter. We still keep it positive. So the absolute value of 69 is just 69. Nothing changes. Now, you might be getting worried, well, what if there's a decimal? Well, whatever's on the inside, we just make positive. So the absolute value of -5.8, well, just the positive is 5.8. Nothing to do there. Just leave it alone. How about -2/3? Well, just make it positive. Can you reduce that fraction? 2/3 can't get any simpler, so no, done. Let's see one more like that, and then I'll end this torture. Let's say I had 0 over -17. And I said negative, so let me fling in a negative there. All right, so the absolute value just makes everything positive. So we have 0 over 17. Could we simplify that further? What's 0 divided by anything? Well, that's just 0. So 0 is the correct answer, not 0 over 17. So be careful. Absolute values, we just make them positive, but if we're able to simplify, we must. And until next time, that's it.